Hi everyone, I'm Ohad Rozen from Bar-Ilan University, and I will talk about enhancing inference models with relational knowledge. This is a joint work with my wonderful collaborators Shmuel, Amar, Shwartz, and Dagan, my supervisor. Transformer-based pre-trained language models such as BERT and GPT have recently achieved human-level performance on standard NLI benchmarks. However, the performance on this complex task is achieved in part thanks to large training sets that facilitate learning of dataset-specific biases and correlations, and thanks to the similar distributions between the training and the test sets that reward such models. This contrasts with humans. We, humans, can learn from a small number of examples thanks to our ability to generalize linguistic knowledge to examples that are new to or infrequent in the training data, as discussed in Linzen's paper. Indeed, previous work showed that NLI models often fail on examples involving various linguistic phenomena, which they are expected to acquire indirectly from the NLI training set. Let's take for example the Hypernymy phenomena. Consider a pre-trained BERT model trained on the multi-NLI dataset, achieving high accuracy on the multi-NLI test set. Now let's take a challenge set where each instance involves hypernymy. Such an instance could be the premise there is a dog near the snow that entails the hypothesis there is an animal outside, or the premise John loves banana that contradicts the hypothesis John hates all fruits. So if we take our model that was only trained on multi-NLI and probe it for its knowledge of the hypernymy phenomenon by testing it on such a challenge set, the result will significantly drop. To fix that drop, we can expose the model to a small number of examples from the same distribution, in this case examples involving the hypernymy phenomenon, thus teaching the model to address this phenomenon. So the model may have learned various specific rules relating to hypernymy, such that dogs entails animals in upward monotone sentences, or fruit entails banana in downward monotone sentences. But what if our challenge set contains facts that the model is not familiar with? Let's look at this premise. Sarah looked at a pangolin, and the hypothesis, a plant was seen by Sarah. Although we had trained the model with multiple hypernymy entailment examples, and it is already familiar with the hypernymy phenomenon, if the model does not know what pangolin means, it won't be able to correctly classify this instance. However, if we could somehow tell the model in real time that pangolin is an animal, then it could probably know that this instance is a contradiction. Humans do it all the time. We easily apply learned rules on new facts, just like in this example. We would like an NLI model to have this ability as well. For that end, we want the model to distinguish between two distinct abilities. One, learning inference patterns detached from their original context, and two, to be able to apply these patterns in new contexts involving different concrete facts. For example, from the training example, Alice ate a banana entails Alice ate a fruit, we want the model to learn the inference pattern that a word entails its hypernym in upward monotone sentences. Then, we would like to apply this pattern to the test instance Bob saw a pangolin entails Bob saw an animal, while telling the model the fact that the hypernym of pangolin is animal. Training a model on every possible hyponym-hypernym pair is incredibly inefficient, and whenever the vocabulary expands, it requires retraining the model. Instead, we propose to decouple the learning of generic inference patterns from that of the factual knowledge. To that end, we have developed InferBert, a method to enhance language models with relational knowledge, the facts, from a knowledge base. In contrast to recent knowledge enhancement approaches such as NoBERT and ERNIE that inject knowledge about individual entities, such as pangolin, InferBert informs the language model about the relation between a pair of entities that are involved in the inference instance. For example, hypernym of pangolin is animal. This approach is agnostic to the identity of the specific entities, allowing the models to learn inference patterns separately from the individual facts involved in particular instances. Entities can refer either to named entities, such as entries in Wikidata, or to common nouns such as WordNet lemmas. To decouple learning the inference patterns from the facts, we directly embed the semantic relations between entities in the text. For that, we use a broad definition of knowledge base as a collection of triplets of the form tail entity, relation, and head entity. For example, pangolin as tail entity, Hypernymy as relation type, and animal as the head entity, and we focus on k different relation types of interest. For each relation type Rk, we learn two embedding vectors. Ehead represents not the head entity itself, animal in this example, but instead it represents the head of the hypernymy relation, or if you wish, the concept of hypernym. Similarly, eTail does not represent the tail entity itself, but rather the tail of the relation, or the concept of hyponym. Let's take another example. For representing the relation R2 between a US location and its state, like Dallas is located in Texas, eHead would represent the head of the relation, which is the concept of state, and eTail the tail of the relation, which is the concept of location. We assume that for a given relation set R, the knowledge base is accompanied by a relation extractor, which takes a text X as input and returns a list of such triplets. Let's take WordNet and Wikidata as our knowledge bases, and the following sentence pair for example. The premise, pangolins have been seen in Baytown, and the hypothesis, some animals were seen in Texas. The relation extractor matches the entity pangolin to its entry in WordNet, locates its hypernym animal in the hypothesis, and creates a triplet with the relation hypernymy. The same for the entities Baytown and Texas, and the location relation extracted from Wikidata. Now that we have extracted the triplets and the relation embedding vectors, we can create a relation embedding matrix R with one embedding vector corresponding to each of the input tokens. So, for example, to represent the fact that pangolin and animals are related by the hypernymy relation, we take the embeddings of hypernymy tail and place it in the index of the first token of the entity pangolins. We also take the embeddings of the hypernymy head and place it in the index of the token of the entity animals. Similarly, for the entities Baytown and Texas, with the relation location, we place the embeddings vector of the location tail in the index of Baytown and the embeddings of location head in the index of Texas. We place a 0 vector in all other indices. To enhance BERT with our relation embedding matrix R, we base our architecture on NoBERT, a work by Peters et al. We choose two consecutive BERT layers, I and I+1, and add a module named scar between them. The scar is based on the NoBERT scar layer and stands for Simplified Knowledge Attention and Recontextualization. We denote HI as the input and HI prime as output. We use a linear projection to project the input HI to the embeddings dimension, and using the matrix R, we add a corresponding relation embeddings vector to each of the projected token representations to create S, an enhanced token representation. We then use a standard transformer block, but instead of using the same projected hidden layer vector at the input to the query key and value, we use the projected hidden layer only at the input to the query, and the enhanced token representations S as the key and value input, along the enhanced token presentations attend the original presentations. We then project the resulted embeddings back into the original BERT dimension, adding a residual connection, resulting in HI prime. After adding the scar layer, the rest of BERT is left unchanged. To evaluate InferBert, we created 4 different datasets, one for each relation type: hypernymy, location, color, for example, Tommy ordered tea and pineapples, and tails Tommy ordered yellow fruits, and country of origin, for example, CEO of Amazon is stepping down, and tails the CEO of an American company is stepping down. More details about the dataset can be found in the paper. To evaluate our method, we compared InferBert to a vanilla BERT model, as well as to 2 recently presented knowledge enhancement models, KBERT, C paper by Liu et al., and NoBERT. For a fair comparison, we made sure that both KBERT and NoBERT get access to the exact same knowledge that InferBert does. We first trained each of the models on the multi-NLI dataset. We further fine-tuned them on a training set that combines all of our 4 challenge training sets, and then tested them separately on each of the challenge test sets. At this stage, our test set included only entities that were already seen in the training set. For example, the sentence pair Bill was born in Lyon entails Bill's homeland is France could appear in the joint training set, and the pair Jane visited Lyon entails Jane has been to France would appear in the location test set, while Lyon and France has already been seen in the training set. These are the test results of all models on the different test sets. We see that the knowledge-enhanced baseline models outperform BERT on all semantic relations by up to 9%. InferBert performs the best, with a gap of up to 10% from the second best baselines, demonstrating our method's advantage over the other methods. To explore the model's ability to generalize the learned phenomena to instances with unseen effects, we repeat the same experiment, but now, at inference time, we replace all entities from the test set with other entities that have not been seen during training. Note that despite not appearing in the training data, these unseen entities do appear in the knowledge bases, and all models have access to this knowledge. Let's look at the test results with unseen entities. For an easy comparison, the results of the previous experiment with the seen entities are displayed in bright colors. Evidently, InferBert shows impressive robustness with hardly any decreased accuracy when facing unseen entities. The other 2 knowledge-enhanced baselines drop significantly by an average of 6 and 9%, comparing to the previous seen experiments, which implies they depend significantly on seeing the test entities already in training time. In fact, when faced with new entities, the 2 baselines' performance gets closer to that of the original BERT, with no knowledge injected. Overall, comparing all of the unseen results, InferBert performs the best, with a large gap from the second highest baseline, up to 20 points, demonstrating its ability to learn and generalize inference patterns and apply them to new relation instances as well as to unseen entities. InferBert is significantly less memory consuming than NoBERT and other methods, which stores upfront the embeddings for all entities in memory. InferBert achieved better performance than NoBERT on the challenge sets, with as little as 1,000 examples per relation in training. Training is more data efficient, as InferBert is not required to learn about specific head or tail entities, but about relationships, which occur more frequently in the training data. To sum it up, we presented InferBert, a generic and efficient method to incorporate relational knowledge into transformer-based inference models. Our approach targets specific inference phenomena that require external relational knowledge, allowing the model to learn generic inference patterns decoupled from the factual knowledge required for a particular instance, which is injected at inference time. Our experiments show that InferBert successfully applies the learned patterns to unseen facts, where other knowledge enhancement models fail. Unlike prior work, InferBert does not require pre-training the language model on a knowledge base and consumes less memory. A shortcoming of our method is that it requires manual selection of the target relations. Therefore, a natural future work would be to expand our method to support a much wider range of relations. Thank you for listening.